So here in this video, we are going to take a look at an example of a beam where we're going to use what we learned about the relationships between load, shear and bending moment to go ahead and draw a diagram directly without having to go through all the calculations. So here's our beam shown with 450 pound load and then 150 pound per foot distributed load. At A and D we have a pin and roller support respectively, and I've already gone ahead and calculated the reaction forces RD and RA. So we can add those onto our diagram. That's our RA. And then here at D, we have this force RD. So there's our free body diagram here for our beam. Now, what we actually have happening here, bear with me a sec, I'll draw a set of axes. Okay, so here we have our shear axis, which is going to be given in pounds, and then here we have our distance along the bar x, which is given in feet. So we know that at RA we've got 200 pound force. So what's actually going to happen to our shear curve is it's going to jump up and basically start here at 200, and then between A and C there's nothing going on, so that's just going to be a flat line. But then we reach this point here, 4 feet along the bar. We've got 450 pound force downwards, so this is going to drop. And that point there is going to be negative 250. Yeah, so 200 minus 450 gives us negative 250. And then we have nothing else happening. So we've got a flat line again until we reach this point here, which is D. So that would be C and D, and this was point A. And then I'll just mark this on now. That's our end of our beam is going to be B. When we reach point D, we've got RD, right? Straight up 850. So from negative 250 all the way up, plus 850 is going to take us to positive 600. And then, what do we say? We said that our shear is the area, the change of our shear is the area under the load curve. So we've got 150 pounds per foot. So what that means is the slope, right? The slope of our shear curve is going to be negative 150. So for every pounds for every foot. So this is going to slope over a distance of 4 feet. We've got 4 feet times 150 pounds, give us 600 pounds total. So over 4 feet, we're going to have a straight line down to 0. And we should reach 0 at the end of our beam. So, so that's how we do it. So there we go. We've drawn our shear curve right like that without doing any detailed calculations. Now, if you want to, you can go back and make the cuts like we did before and look through each section of the beam, and you should confirm this result that we have here. Okay, so hopefully that's clear how that works. Basically, anytime we have a point load, our shear graph is going to jump by that amount, and then anytime we have a distributed load, our shear graph is going to, the slope of the shear graph is going to be negative the value of the load curve. So our load curve here has a value of 150 pounds per foot, and it's a constant value, so we've got a constant slope of negative 150 on our shear graph. That makes sense? If we're in a situation where our slope, we had an actual slope on our load curve, if we had a distributed load that was sloping like this, it's not very well drawn, but then if that was the case, then we would expect a curve on our shear diagram. Yeah? Okay, so from that, we can actually go ahead and use this shear graph to draw our bending moment. So we've got our bending moment there in foot-pounds, and our distance x still in feet. And let's just carry these lines down, these little dotted lines that show the positions along our bar, so we can use those kind of as a reference point still. So what we're going to have is the essentially what we're going to do is we're going to integrate our shear graph to find what our bending moment would be. Now, just an important point to note here is if we have an applied bending moment, if we had along our beam somewhere an actual applied moment, then we would see a sudden jump in our moment graph the same way we do when we have these transverse forces applied in our shear graph. But because we don't have any applied moments, we shouldn't see any discontinuities in our moment graph. So let's take a look. The area under our shear curve, here we've got a distance from A to C of 4 feet. from C to D of 8 feet, and from D to B of another 4. So here, this area here is going to be 200 times 4, so that area would be 800, yeah? This area here, we've got negative 250 times 8. So there we have negative 2000. And then here, this area is a triangle, so we've got half the base times the height. So there's going to be 2 times 600, so that area is going to be 1200. Now you may notice that these are all added to 0, right? 800 plus 1200 is 2000, minus 2000 is 0, which is great. That's exactly what we'd expect. So to go ahead and draw our moment graph, well, the value, let me just write this down. The value of the shear is giving us the slope of the bending moment, yeah? So that is going to be key for us. So we found those areas under each part of the curve. So between A and C, our bending moment, well, we don't have any applied bending moment at A, so that should start at 0. And then it's going to have a positive slope, a constant slope, yeah, because we have a constant value of our shear, which means this is going to be a constant slope. So it's going to slope up with a slope of 200, and it's going to reach 800 foot-pounds right here, yeah? And then we're going to have a constant slope of negative 250 over this whole thing. So from there, it's going to slope down. Let me just, this is going to be a little harder to draw. So we'll call that about here is going to be, now bear in mind, okay, it doesn't mean that the value of the bending moment here is not going to be negative 2000. It's going to change by negative 2000, which means the value will be negative 1200, yeah? So the area under the shear gives us the change in bending moment, okay? So 800 to negative 1200, that was actually pretty good considering how I thought that line drawing was going to go. Now we know our increase is going to be a positive 1200, so it's going to get us back up to 0, but this time we don't have a constant slope, right? Here we had a constant slope, so that was a straight line. Between D and B, our slope starts out at 600 and it ends up at 0. So we start with a positive slope and then we end up with a 0 slope. So it starts out, that slope's going to start out positive, and then gradually, let me redraw that. It's going to start out positive and then gradually become less positive until our slope hits 0. So we've got straight line here, straight line there. Sorry, that one didn't go so well. And then we're going to have kind of a more parabolic shape coming up here, and that's what our bending moment is going to look like. So our absolute maximum magnitude of our bending moment here is this 1200 foot-pounds, or negative 1200 foot-pounds, and there we go. What was that was what we were looking for. So there we go. We were able to draw those graphs directly without any of the calculations, just based on using our own incredibly powerful brains. So have a look now at trying some of these examples yourself.